Now that we have learned about the first three practices of the next generation science standards, and how to use these reference documents to support our alignments, let's dive into the remaining 5 practices. We will learn some clues on how to recognize them, and also learn some ways we can make sure our activities actually assess these skills and processes of science. Practice 4, Analyzing and Interpreting Data. Scientific investigations produce data that must be analyzed in order to derive meaning because data patterns and trends are not always obvious. Scientists use a range of tools including tabulation, graphical interpretation, visualization, statistic analysis, etc. To identify the significant features and patterns in the data, scientists identify sources of error in investigations and calculate the degree of certainty in their results. Modern technology makes the collection of large datasets much easier, providing secondary sources for analysis. Engineering investigations include analysis of data collected in the tests of designs, which allows for comparisons of different solutions and determines how well each meets specific design criteria. That is, which design best solves the problem within the given constraints. Like scientists, engineers require a range of tools to identify patterns within data and interpret results. Advances in science make analysis of proposed solutions more efficient and effective. Be careful with this one. Often we see a data table or chart, we jump to the conclusion that it would be this practice. But sometimes, like the images, the data on the test item is just for show. When test items are calling on this practice, it will ask the student to go beyond just referencing a chart. It will ask them to do some analysis or interpretation of what the data means. Sometimes you can have a question that asks students to analyze without the use of a data table or graph at all. Instead, there can be a description of data. Think of a story problem about the weather. If the question asks them to treat the description as data and reason with it, then this skill is being drawn on. Another way to think about this practice is that it's not always a number. Qualitative observations are included here too. To extend on this weather example, if students were asked to look at a set of cloud formations to make a logical inference about the upcoming forecast, they would be analyzing and interpreting clouds and their patterns. The next one is using mathematics and computational thinking. In both science and engineering, mathematics and computation are fundamental tools for representing physical variables in their relationships. They are used for a range of tasks such as constructing simulations, solving equations exactly or approximately, and recognizing, expressing, and applying quantitative relationships. Mathematical and computational approaches enable scientists and engineers to predict the behavior of the systems and to test the validity of such predictions. When you see a need for students to use math, it's a good bet you should at least consider aligning to this practice. However, be careful. We are really looking at computational ways to understand the phenomena in the world around us. This doesn't always look like a math equation. And sometimes when we are looking at a math equation, we aren't really using the math to understand things. Always stop to think about why we are using math. The end products of science are explanations, and the end products of engineering are solutions. The goal is the construction of theories that provide explanatory accounts of the world. A theory becomes accepted when it has multiple lines of empirical evidence and greater explanatory power of phenomena than previous theories. The goal of engineering design is to find a systematic solution to problems based on scientific knowledge and models of the material world. Each proposed solution results from a process of balancing competing criteria of desired functions, technical feasibility, cost, safety, aesthetics, etc. The optimal choice depends on how well the proposed solution meets the criteria within the constraints. Many questions that draw on this practice are open-ended. Be careful, though, to be sure that students are being asked to explain a phenomena, not just explain their thinking. And be sure with design solutions that they're designing a solution to a problem. Explanations are about demonstrating our understanding of the world around us, not providing reasoning or evidence for our claim. Now we are at the engaging an argument from evidence. This practice is one of my favorites and has a lot of constructivist and cognitive science research to support how this practice supports student learning. Argumentation is the process by which evidence-based conclusions and solutions are reached. In science and engineering, reasoning and argument based on evidence is essential to identifying the best explanation for natural phenomena or the best solution to a design problem. Scientists and engineers use argumentation to listen to, compare and evaluate competing ideas and methods based on merits. Scientists and engineers engage in argumentation when investigating a phenomena, testing a design solution, resolving questions about measurements, building data models, and using evidence to evaluate claims. In order for a question to align to this practice, it's important that students are providing an evidence-based argument. Most often, this will require an extended response type question. However, it's possible to have something that gets at this with multiple choice item format, especially questions that are asking students to identify the appropriate evidence for a specific claim. Clearly, this is assessing one part of the larger practice. However, it still could align here. Here's a helpful, simple rubric taken from the instructional strategies to support students writing scientific explanations. This rubric helps identify the written ability for students to meet the criteria of argumentation. There are many other sources, Toulmin, Osborne, and Sampson, who has the argument-driven inquiry model, that provide explicit steps for argumentation, including rebuttal, that are not included here. But for illustrative purposes, this is a very handy visual graphic. Finally, obtaining, evaluating, and communicating information. SEP 8. Scientists and engineers must be able to communicate clearly and persuasively the ideas and methods they generate. Critiquing and communicating ideas individually and in groups is a critical professional activity. Communicating information and ideas can be done in multiple ways, using tables, diagrams, graphs, models, equation, as well as orally, in writing, and through extended discussions. Scientists and engineers employ multiple ways to obtain information that's used to evaluate the merit and validity of claims, methods, and designs. This is a really huge practice. There's so much within it. As you think about your alignment work in this practice, I'd caution you to not use this as an umbrella for everything, as it would get too large. Really, almost anything could be rationalized to fit here. It can be tempting to stretch this to cover any questions that don't fit anywhere else, but before you align to this, ask yourself, if a student gets this question correct, does that really tell me about their ability to obtain, evaluate, and/or communicate information? Why? How? If you don't have an answer to this, then it probably doesn't align here. And that's a great question to ask yourself about all of these practices. Anytime you're aligning to one of the practices, ask yourself those how do you know questions. If you don't know, or if the answer to this line of questioning does not tell you anything about what the student must know or do as the criteria for the practice, then challenge yourself with the question, why am I trying to align it here? If you can't justify your alignment, or it doesn't make sense to the dimensions criteria, then you probably shouldn't align it there. This interactive graphic is from the UC Berkeley. It is very helpful in discussing the components and the real process of science. It debunks the misconception that science is a linear or stepwise process. I think this model summarizes the doing of science or the practices very nicely, and if you have never checked out this graphic or site, I encourage you to do so. Another resource that might help bundle up these ideas is the Next Generation Science Standards Appendix H, The Nature of Science. This document identifies the ideas that are most closely associated with the practices in blue, and those most closely associated with the cross-cutting concepts in green. Now that we have learned about the first 3 practices of the Next Generation Science Standards, and how to use these reference documents to support our alignments, let's dive into the remaining 5 practices. We will learn some clues on how to recognize them, and also learn some ways we can make sure our activities actually assess these skills and processes of science.